And welcome back. Now this week we're going to talk a little bit about memory compression. Well, EEPROM memory compression, because I was talking to an engineer friend of mine and he had to compress lots of information into memory, but then again he was using a 32-bit microcontroller with loads and loads of memory, so I guess space really wasn't that much of an issue, unlike us where we are severely limited with our EEPROM. And if you've got a few phrases or sentences that you need as part of an instruction set or warnings, a bit like these ones down here, look. Now these are the ones, for example, that he was using or gave me as an example. You know, he was talking about lifts, so you might say doors closing, first floor, second floor, however many floors there were. Yes, all right, you'd probably have the word floor as one word. But even so, it's got to come up on a little display, staying clear of the doors, reception desk, whatever it's going to actually display on the LCD inside the lift. Now what this got me thinking about is how we could compress the memory within any Arduino style board, because after all the memory is quite limited on here. I think it's about, what is it, a K on the standard Arduino? That's a 328p, something like that. I'll check it out in just a sec. And I thought, well, okay, I'll remember something about this, and started reading up on the internet about Radix 50, and it seems, hey, this is actually pretty easy stuff. We can do this very simply. So if you've got a requirement for compressing some data, this is it. And even if you haven't, do keep watching, because some of the techniques we use are quite interesting, and you might decide to use them anyway for whatever device you have. So let's chug on, and we'll cover the theory pretty quickly, and then we have got a sketch and a quick demo on here already actually. So we'll cover this pretty quickly. Yeah, I know, I say that every time, don't I? Okay, right then. First things first. What are we talking about when we're talking about a Radix 50 compression algorithm? Well, basically, it was invented in the dawn of time by DEC, Digital Equipment Corporation, and they learnt pretty quickly, because back then, of course, memory was as precious for sort of large computers as it is for us today with the little ones. So they invented something called Radix 50, and if we look at the browser window, here we are. Wikipedia's got quite an interesting article. Let's take me off for a sec. There we are, bring this in line. Right, there we are. So now the interesting bit on here is, in fact, okay, there's a bit of background here, but the interesting bit we need to look at is, in fact, not 36-bit systems, not 18, but 16-bit systems. So this is the theory, and we'll go through this, and believe me, it's a lot easier than what it looks here. And we're going to replicate this so that we can say we can encode these 40 characters. I mean, it doesn't have to be these 40 characters exactly, but you'd probably want, you know, A to Z with a space and 0 through 9. And then we have 3, well, other characters we can use here. So let's think how you would actually use this in real life. If you have a requirement to program an EEPROM with a significant amount of data that you'd like to compress down as much as you can, the idea is you'd run a program pretty similar to what I've got on here already, just to program the EEPROM on that chip. Now it could be an external one, but I'm thinking more internal, get as much space as you can, but of course it can be used for an external one as well. You might find that perhaps you don't need an external EEPROM if you can compress enough into that onboard stuff, or you can buy a smaller chip that you connect up externally via I2C or something, rather than getting a big one. So let's see how it all hangs together. Right, back to the workbench. Here we are. Right, enough of those little messages. So here we have that same table written out, and what we want to do, I'm going to write in black pen, and I'm going to zoom in a little bit so you can see it. Just let me zoom in this camera just a tad. That's it. Right, now first of all, this table represents the characters in here. The 40 characters overall. We're going to ignore these ones that are blank in the middle. They don't represent a space. The space is in fact up here. 0, 0, 0, 0. And well, let's just take it from there. Now, let's think about first of all a standard Arduino type byte. Yes, or a byte can also be known as a character, can't it? So a byte is equivalent to a char, and it takes up 8 bits. Now, if you're going to store one of these, which is a sort of a subset of the ASCII characters, but as I say, we can include many more, ASCII characters can be represented in 6 bits. So if you're trying to squeeze lots of data into, let's say you had an EEPROM of, I don't know, 30 bytes, right? And some chips do have a very, very small amount of EEPROM, just for sort of little flags more than anything else. Now you might be thinking, well, hang on, I've got 6 bits here that could represent any one of these, as you can see, because you've got the most significant byte at the top, these 3 bits, and the least significant byte, LSB, across the top. So for example, R, just happens to be the first letter of my name, would be 010010. So we're thinking, hang on, I can represent an ASCII character in 6 bits, but I'm putting it into an 8-bit character. That means I've got 2 bits that are like, well, not used. And then we come on to the next character, which is, my name would be an A. And once again, we're using 6 bits and having 2 bits totally unused. Now you multiply that a few hundred times and you'll see that the efficiency is not going to be great. Now, of course, on your computer or your phone or something, whether you've got 2 bits or not left lying around after you've stored the characters is of absolute no consequence whatsoever. But in the embedded world of microcontrollers, it can make all the difference between a viable product and one that just costs too much money. Imagine, for example, your washing machine manufacturer. They decided on a particular chip. It probably wouldn't be an Atmel, but you never know, it might be. And they have to have a certain number of messages on here, a bit like those lift messages, that give you instructions on what to do when you're loading the washing up and all that, or perhaps to give you some warning messages saying your drum's too heavy or no water or add softener or something like that. And they've decided that in fact to try and put those messages into the chip they've chosen just wouldn't be viable. There's too many characters to make it meaningful to the user. After all, the average user doesn't like abbreviations, they don't like codes that they then got to look up in a book. So they might think, that's a shame, because we could have made that controller with that chip and got our cost down to, you know, $2 or $3 a board, but now we can't because we haven't got enough space. Except if they use a technique like this, which I'm sure they already do, then they think, hey, we can squeeze some more characters into that EEPROM. But how do you do it? If we're putting a single character into a character byte, how do you get more in? After all, you've got 1 in, you've only got 2 bits left over. What do you do with it? Well, the clever thing is you don't use 1 character or 1 byte. You in fact use 2. Now, if you've got 16 bits, you can see that 2 bits would be 12. So times 2 equals 12 bits. And that leaves you 4 left over, doesn't it? 4 remaining bits. Ooh, trying to watch the screen and write is impossible. Right, so you've got 4 bits left over. And because we've done something clever, that's enough, with a bit of alteration of the last couple of bits here, to hold 3 characters. So what you've actually got is 3 characters into 2 bytes. Right? So that gives you an immediate saving of 33%, doesn't it? Which could be quite significant when you've got a few hundred characters to store, or indeed, you know, a few dozen messages or lines or warnings or whatever. So how's it all going to work? Well, let's continue with the example that I was going to show you anyway, which was encoding. Well, to begin with, let's just say the first 3 characters of my name. Now I'm going to use my notes that I did for this, because I worked through an example before I started coding, just to make sure I had it clear in my own head from that Wikipedia article, don't forget, this one here. So I just checked that what I was doing here and reading the instructions all hung together, and of course it did. So if we're saying now we want to encode the letters R, A, L, and according to this, that's 3 characters, and that should fit into 2 bytes. Now, what do we have on the Arduino world that's 2 bytes long? Yes, you've obviously got there before me. 2 bytes is, of course, an integer. Right? Every integer on an Arduino is 2 bytes long. You didn't know that? Well, think about this then. But next time you're doing your 4 count equals 0 to whatever, if you're using an integer, that's going to take 2 bytes, which you might not need. If you only need up to 255, you're better off actually using a char, which is 1 byte. Okay. Anyway, that's code memory, not EEPROM memory. So let's carry on with this. So we're looking at RAL. How do we encode that into 2 bytes? Well, going by this table here, this lookup table, the R is 010, and the least thing of it is 010. So we've actually got for the R 010, 010. Now, quick as a flash, you'll no doubt be able to convert that binary representation of a character into a value. And we say, right, 010, 010 is in fact 18. Why is it 18, you ask? Well, these are the bits of the byte. Remember, we're not using the first 2 bits now. So this is the 1s, these are the 2s, 4s, 8, 16, 32. That's what they all represent. And there's 1 16 and there's 1 2, which equals 18. Okay, so well and good. How's this getting us anywhere? Well, what we do now, for the very first character of our 3 byte triplet, we multiply it by 40 to the power of 2, which, although this is called radix 50, you could really say this is a variant of that, and it could be called radix 40, I suppose, because there's 40 characters, and that's what we want. Now, 40 squared is 1600, so times 18 equals 28,800. Okay, hold that thought. Let's move on to the next character. So A, by looking up into our lookup table here, is 000001. Now, I'm sure you don't need me to tell you what that's equal to, so that's a 1. This time we don't multiply it by 40 squared, we multiply 40 to the power of 1. Now, 40 to the power of 1 is in fact 40, but it's the pattern that's important, so it's squared first, then to 1. So 40 times 1 is of course 40, and we just add that on to this column here. And then finally, the third letter of my name, L. So looking it up here, L is 001100. So 001100, and that is 12. Looking at this list here again, we've got 1, 2, 3, the third byte, which is 4, and we've got an 8, so 8 plus 4 equals 12. That's what we interpret that as humans, times 40 to the 0th power. Now, anything to the 0th power is in fact 1, so we're not too worried about, it's just 12 basically. But I'm showing you that to show you this pattern. So we add in 12 there, and then add those up. Now, those added up together come to 28,852. As I say, I'm using my crib notes because I'm not going to make a foolish error on video. So 28,852, will that fit in an integer? Well, yes. Just 1 minute. It will fit, but remember these values, could be a lot higher than this. This A character, the second one, happened to be a value of 40, which is pretty low, isn't it? And 12 is pretty low. What if we'd had, RRR, for example? Yeah, that is big, isn't it? And that would easily go beyond a value that would a standard integer would hold. So we are looking at, I'm going to write this bit in red because this is important. You get this wrong and it won't work. It's not just an integer, it's an unsigned integer. Okay, that's the important bit. Now we can hold up to 65536 in an integer, unsigned integer. So no matter what letters we choose here, any 3 of these multiplied to 40 squared are still going to fit. So having got 28852 now to represent the letters RAL, and how do we decode this? Okay, we're starting off then with this 28852 that we've just read from the EEPROM as the first integer 2-byte value. Step 1, we say take the value and take the modulus. Modulus is represented by this funny percent sign. So 40 divided into 28852, remainder 12. That's what the modulus is, the remainder. Great, so 12 is in fact the rightmost character. Bear with me. We're now saying 28852, the original value, minus the 12 that we've just taken off, gives us 28840, divided by 40 equals 721, modulus 40 equals 1, 1 being the middle character. And the third step, we're saying we're now end up, remember, 721, so 721 minus the character we've just extracted, which is only 1, 720, 721 minus 1, divide by 40. There's no need to do any modulus at this point because it's always going to be the remainder, 18. 18, 1, 12. Does that ring a bell? Well, if we just look back on the previous page. So on the previous page we were encoding 18, 1, 12 to get that 28852. So there we are. That's all we had to do to get our values back out again. And if you think this looks a bit of a mess, that's because of my handwriting. I think it's about time we looked at the sketch really to see really how simple this is to do. Right, this is the sketch. Now, first of all, if you remember on our lookup table, we wrote that, or the web page displayed that somewhat differently to we got it in here. So if we look at the browser just briefly, you notice that this is done as a sort of a table with most significant and least significant bits, because that's the way logically it's going to be encoded. And indeed that's how we did it in our little table here. But in reality, because the computer just doesn't care whether it looks nice on a piece of paper or not, what we're saying is we're just going to encode our values as a big long string, starting with space, which, hang on, let me just, there we are, look, as we start with the space, and we're just going A, B, C, D, E, F, G, and then we're just moving down to the next one, H, I, J, just as you would do normally. Now, I've stopped, as it happened, after this byte here, and in fact, what have I done? I've got exclamation mark, comma, and a decimal point, just for proof of concept, really. But that is what it's representing, isn't it? Now, you could put these in different order. If your particular messages used different characters much more often, for example, if you're using the Cyrillic alphabet, you wouldn't be using these, would you be having something else? Or German characters, for example, would contain different letters with umlauts and things, which might mean you'd have to use the additional method of getting some characters, but that's for another day. Right, this is our lookup then. So that lookup represents this table down here. Now what we're saying is we're first of all going to just encode the first 3 letters, like I said. Right. Now, obviously, because we're encoding 3 characters at a time into 2 bytes, we really do need it to be 3 characters in length. So what this little bit here does is just make sure that the chunks are 3 characters long, or at least they're multiples of 3. When we come on to this much bigger string, which frankly I have no idea how big it is, all I know is that it fits into 60, we're going to make that a multiple of 3 by adding on 1 or 2 spaces at the end by this little bit of code here. That's all that does. And in fact that's the approved way of doing it, just add a space, because you're not using any more characters by encoding spaces at the end. You've got to use 2 bytes anyway, even if you're trying to encode a single character at the end. So you add 2 more spaces and encode the 2 bytes as you would normally. Right, now the return array of numbers is obviously going to be 2/3 of the length of the string that you're encoding. So in this case, RAL, it's 3 bytes. 2/3 of that is going to be 2. So the return size is going to be the length of the string divided by 3. But remember, yes, that says 3 divided by 3 equals 1, but remember that an integer takes 2 bytes. So it's one lot of integers, which is 2 bytes. Okay, so that's multiples of 2 really. Okay, so here we return, create the return array size, just so we can use it a few times. And here we say encode that string, whatever it is we're passing it into. Now, to prove that what we're encoding we can decode again without any smoke and mirrors or anything like that, we're saying, right, here's our return list of characters, and in this example it'd just be one single character, and then we're going to run a decode routine as well, both very simple, and then just print some stats. So this is all set up and you know, paraphernalia like that. Let's look at the actual code to actually encode stuff, and it's pretty small. Here it is. That's all there is to it. So what we're saying is we're taking in an array here of characters. Now, you could have said here, I'm using a pointer. Why? Because arrays are always passed to functions like this as pointers, just regardless of what you might do. So when we're saying in here, encode test string, well, string here, the test string is this one here, and it's an array of characters. Yeah, so because it's an array, C++ says, well, you can call this, if you like, unpacked message, square brackets, and knock out the pointer reference, but it says because you're an array, you are a pointer reference regardless. Okay, ditto the array for integers that's coming back, and that's a C++ language requirement that arrays are always passed as pointers. Why? Well, let's think about it. If you've got an array, the very fact you're using an array probably means you've got a fair bit of data, more than just a couple of bytes. Now, if you're going to pass by value, that is a copy of that data to an underlying function, well, you're having to duplicate that rather large chunk of memory. And memory is the one thing we're short of, I think, as we've already established. So C++ says, nope, arrays are always going to be passed by reference, not a copy. It's a pointer to where that variable is actually defined, which does, of course, mean you can update it. Well, obviously, we don't want to update our incoming string to be encoded, but we do want to update our return array with our list of integers. So that's quite helpful, isn't it? Because you cannot return here an array from a function. There is no mechanism in C to return an array there. So this is the way to do it, as a pointer to an array. Okay, a little bit of C++ language knowledge there for you. Right, okay, what are we doing here then? Right, now remember, I've actually got unsigned everywhere like this, like unsigned, unsigned, because if you don't put unsigned, by default, it takes it as a signed integer, which means you'll end up with problems within this code. Because once you get beyond 32 something or other 32,000 something, you flip that first bit in your 8-bit byte, which tells it that it's negative. It'll still work, because whether that first bit is set or not, and we interpret that as a negative value, to you, when you're debugging this, it'll go, why have I now got minus 23,496 in there? When you haven't. You've actually got a much bigger value than that. It's not minus anything. Okay, so keep the unsigned on. And in fact, that's good practice anyway. And it's a pity that the standard Arduino IDE doesn't sort of warn you a bit about that, really, because I think people just stick in int this and int that without realizing it's a signed value, which you don't need in loops like this. And in fact, this IDE of mine will give me a warning that if I didn't put unsigned there and then try to say count less than 4, it will go, hang on a minute, you're comparing apples and oranges here, one's signed, one isn't, what's going on? All right, so unsigned is the way to go. Right, first thing we do then, we say, in our little lookup table, the A to Z bit, right, with a space at the front, it says look up where the first byte of our message comes. So the R, right, it's looking up where it is in that list. So if we go right to the top, we go, right, where is R in here? Oh, there it is down here. That's the nth character along. And as it happens, we decided it was the 18th character along in front. Okay, so it says, okay, the child location is 18th. As this is the first character, we're going to multiply it by 40 to the power of 2. then move on to the second character by incrementing that count value here. So the second character will be an A, and the A is the second character in, and it'll multiply it by 40, and then the third one is just the actual value, the nth one along. And I've added in the fact that yes, we do sort of multiply it by 40 to the power of 0 just to show you this sort of pattern really, but it is superfluous. We wouldn't need to do this. This is just taking up well, processing power and space, unless the optimizer optimizes that away, but I don't know, I suspect it wouldn't, but you never know. Incidentally, this little caret, which we in the real human world use that to mean to the power of, does not mean to the power in C#. There is a power, POW, function to put things to the power, but that requires floats and doubles, and it's just we don't want to do any of that here. We want precision, so it's better just to type the thing out longhand 40 by 40 and 40 and whatever. So anyway, then it says now we've got our value, put that value into the next space or the next position in our return array. That's what the iteration plus plus is. So if we were on 0, put it into 0 and then add 1, ready for the next one, and put the packed 3 character value 28,000, what was it, 28,852 into that array location. Okay, now that's pretty simple when you think about it. There's more comments and everything else than actually doing here, especially when you consider I've added in things that don't actually need to be done. They're only in here for demo purposes to show you the pattern. Right, the decode is just as simple. We're taking in, look, here we are, an array called test packed. Now you could have it as star test packed because it is a pointer again to an array, or as test packed with square brackets to indicate it's an array. Use whichever you think you would understand more, but have no illusions that is a pointer. Yes, you are using pointers whether you like it or not. And in here we're giving it the length of that array, because otherwise how's it going to know? We have to work it out somehow, and we already know that it's 2/3 the length of the message we're trying to encode or to pack, so we might as well pass it in here. This just prints out the list. That was a bit of debugging for me to make sure that the stuff coming in was in fact what I expected. A couple of strings here to take the messages for final output, the output messages for the 3 characters, the 3 character chunks, the final message is the full long thing. And then in here, all we're doing for 3 characters worth, we're doing basically what I said here. We're saying take the modulus of 40, the remainder, and output it, put it into our string, subtract it and from the original value and divide by 40, and then you can just go around the loop of wings. The next thing it's going to say is take the modulus and output the character, which would be in this case 1, subtract that value from the original or the remaining value that we've got and divide by 40. There it is. Look, I mean, it's so simple, isn't it? The maths is almost non-existent. And then to display the value, and that's the end. Should we see how it works? I think that'd be a good thing. And then we'll put that big message in. You'll see how ridiculously simple it is to do, if not to actually say that word. Right, Arduino's plugged in and running this in this exact program, no smoke and mirrors or anything else. So let's reset it to show the output. Nice and quick. So what it's saying is we've started the array encoding, we've finished the array encoding, and we've ended up with a single integer of 28,852, exactly as per our example down here. We've then stuffed that into the decode array, 28,852. It says, well, that comes out as RAL. I've finished. And then a bit of stats. The original text was 3, the new text is 2. We've saved 33.33%, which of course is fixed. That won't change. Yes, all right. Only realised once I'd written this in the code that it's always going to be the same. Why am I outputting it? But there we are. So that's it really. It's packed RAL into that integer value to save us a byte in just that little bit. Now obviously you wouldn't do that for a 3-byte string, so let's put a slightly longer one in. We'll scroll up to here, and what we'll do, we'll make this a little bit bigger. Excuse me while I fiddle about with the keyboard. Right, I think that's okay. Let's upload. So keep your eyes on this window here, because that when that clears, that's when it will start running. Oh, building, launching. Yeah, off you go. There we are. Go. And there we are. Now what we can see here, of course, is that there's a whole string of characters now, and we're decoding them all exactly the same way. And it says Ralph Bacon is an Arduinoite, I most certainly am, who has a YouTube channel! Exclamation mark. Indeed, and that's what we put in to begin with, just to prove that it works. Now, as I said, the encoding would probably be done totally separately from the decoding in the real world. You'd encode all your messages with a separate program, this one potentially, with a few tweaks to make it right to actual EEPROM locations. But your decoding would then be done by the, I don't know, let's call it the real program that is doing stuff and requires those messages. There we are, easy peasy. I don't know what else we can say about it, except this is one mechanism for saving EEPROM space. You may think that having a couple of lines of warnings doesn't warrant it, and it most certainly doesn't. If it fits into EEPROM as it stands, fine. But if you're struggling to fit it into a smaller microcontroller of the Arduino family, the Atmel family, a tiny 25 or something, 85 rather, or indeed a 25, you think, or you've got loads and loads and loads of messages that you just can't seem to cram in, and you're using abbreviations and stuff like that. This is one of the ways you can save space. Great. I'm going to put this sketch up and that link to the wiki page, and you can play about with this. And as I say, even if you haven't really got any interest in compressing stuff at the moment, I'd certainly recommend that you just download it, run it, see how it works, and then that will lodge itself somewhere up here in your memory. And maybe in a year's time or 5 years' time, you'll think, I know how to do that. I read that somewhere, or I watched it. It's all good background reading. And of course, we've taught you that passing arrays to a function always comes in as a pointer reference. That is, a pointer to where the values are, not a copy of the values themselves. Okay, right, that's it. Done for today. Hope you enjoyed it. A little bit different to what I normally do, but there we are. It's all good, interesting stuff, isn't it? Great, well, there's plenty more videos to watch, so thanks very much for watching, and see you in the next video. I hope you're finding these videos useful and interesting. There are plenty more videos to choose, and a couple are shown below. And if you'd like to subscribe to this channel, just click on my picture below and enjoy the rest of the videos. Thanks for watching.